Alright, in this section here we're going to be going over relations and functions. Now, this is one of my favorite concepts in mathematics, and that is relations. Because mathematically speaking, generally we can use this in a lot of different ways. And I draw treasure maps, and I've highly I guess you could say, rely on this concept right here when I'm trying to write a coded message. And I'm just going to bring up my treasure map for the heck of it. Well, this particular treasure map here is I do geocaching, and when I do a geocache, I go all out when I make one up. But anyhow, just kind of give you an idea of anyway my treasure map here. I use the concept of relations a lot, and maybe you'll get an idea of how maybe I'm using it. Oh, and by the way, it's at huntforthecash.com, and I do have one at cash.com also, but anyway, hunt for the cash. Okay, we better get back to this. I kind of touched on, I think, in a previous section, what a relation is. Now we're going to talk about it mathematically speaking, just using the real number system. A relation is, you can look at a relation as a set of ordered pairs. And so I'm going to label my set S, and and I'm going to just write in some ordered pairs here. Okay, so in a previous section I think we talked about ordered pairs and so forth. We're going to get into the details on this stuff coming up. So here's a finite set, and it just has three ordered pairs in it. Well, this is considered to be a relation. Okay. Now there is a way to construct this set. In other words, there's a relationship between 1 and 2. In other words, 1 is related to 2, 1 is related to 3, and 1 is related to 5. So it's kind of like how you'd say that. And there's a discrete math course where they kind of labeled this as like 1 with an R, saying 1 is related to 2. Some certain relations have properties like 2 is related to 1 and 1 is related to 2. It's the reflexive property. We're not going to get into all those properties. That's more of a different course. Okay, but there is a special kind of relation that we mostly focus on, that we're going to be mostly focusing on in this course. I want to get back though to the treasure map real quick, because I just want to touch on that, and then we'll leave it alone and then work strictly on the set that we're going to mostly be working with. That'd be the set of real numbers. But take for example, on my treasure map, let's say that I have a object that's got 3 sides, and another object that, let's say, has 3 sides. In other words, these are all triangles, and another object that has 3 sides. So these are all different triangles here, but the deal is that they all have 3 sides. Okay, and I'm just going to label this as triangle T1, triangle T2, and triangle T3. And so we would say that this set here is the set of triangles. For example, T1, T2, and T3. Now, I might say that T1 is related to T2 if, in other words, this object's related to this object if they both have 3 sides. Okay, so we'll define our relationship as 2 objects, object 1 and object 2, are going to be related if Okay, if they have three sides, let's say, or I could just say if they are triangles, right? That should be an S if they have three sides, or triangles. Okay. So in other words, if I were to if I had to write this out, we'll use a different T here. In other words, T1 is related to T2 because T1 has three sides and so does T2. So I would say that T1 is related to T2. But I could also say that T2 is related to T1. And of course, T1 is related to T3. And T3 is related to T1. I'll have to continue this down here. And T3 is related to T1. And of course, we got to go through all the others. T2 is related to T1. And T1, oh, I already did that. T1's related to T2, T2's related to T1, T1's related to T3. Oh, T2's related to T3, and T3 is related to T2. Is that all our possibilities? 3, 2, 1, 6. Yeah, T1, T2, T1, T3, and T3, T2. Anyway, so if we had to write this out as a set of ordered pairs, this is what our relation would look like. Okay. Anyway, so this is generally speaking, and we defined our relation to be if two things had the same sides, same number of sides. I can also, there's something like in my treasure maps I use a lot of, and that's compound words. For example, I would use, like, for example, sunrise, let's say. Okay, so that's a compound word. Let's break it up. Sun and then rise. Okay. Sun is related to rise if you can put them together and make a word, right? But rise is not related to sun because, so this doesn't have the reflexive property. Sun is related to rise. So if I had to write this as a set of ordered pairs, I would say sun is related to rise. But it wouldn't be the other way around. That's if we could make a compound word, make a word out of this, sunrise. So this is like one of my secrets here. There's lots of ways you could define, you can make tons of relations. For example, I might have some object drawn on my map over here and some object over here. And if these two things are related, then a line exists between them. A line passes through both of them. So you would have to find what is this relationship, and then the clue would be that there's, some kind of imaginary line drawn through it, and maybe this is where the treasure is located, somewhere in the middle right there. Okay, so one of my secret techniques there for coming up with clues on a treasure map. But this whole idea really brings out a lot of creativity in one's mind. You can define your relation any way you want. It doesn't matter. There's no set rules on that. You can define it any way you want. You can define, for example, I might have an object and it's colored red over here, some object, and then I have another object and it's colored red over here, right? And I throw in some object that's drawn up over here. But these two objects right here, you might define your relation to be that these. So we could say that the two objects are related if they're both the same color. In other words, this object up here would be related to this object because it's red, and of course this object would end up being related to this object. Tons of ways to define things. You could, let's say there was an object here and an object over here. And let's say that they were at some particular angle. Okay, you could say that these two objects, or object 1 is related to object 2 if object 1 is to the left of object 2 and at some particular angle. Okay, but is object 2 related to object 1? No. Okay, in other words, I'm reading this as like this object here would be related to this object here. Okay, that's the way I'm reading that. So you'd write this ordered pair, but we define it as being to the left, and let's say at some angle 45 degrees here. Let's say from the horizon or something. Anyway, man, there's every kind of way you can imagine to define a relationship. Anyhow, let's get back to the math here, even though that is math. Believe it or not, that's math. Let's clear the whiteboard. And let's look at something else here. I really like to talk a lot about that. I could probably write a dissertation on that, especially when it comes to drawing treasure maps or just art in general, that you're trying to convey some secret message to somebody. And if they know the relation, only they will understand it. All right, let's look at this. Now I'm going to write this as a set of ordered pairs here, and I'm going to look at this relationship here. And of course we're keeping these nice and short. You know, there could be an infinite number of ordered pairs in here. This particular relationship, this is a special kind of relationship, and this relationship is a function. Okay, and here's the reason why. These numbers, these first coordinates here, are all different. Notice all the first coordinates are different. And if these are all different, we can consider this relation to be a function, as long as these are all different. Okay, we don't care about the second coordinate. Alright, second coordinates could be the same, but if the first coordinates are all different, then this is a special kind of relation, and this relation is known as a function, and this is of course what we're going to mostly be working with from here on out. Now I'm going to write up two sets here. This is going to be the set with 1, 2, 3, 4, ... let's say up to 10. Put 10 in here, and then we'll call this the set Y, and it has, let's see if you can see a pattern. There's a pattern going on here. Okay, and I'm going to once again just label this, what should I label this? I'm going to label this as SQ. And what I'm going to do now is the first coordinate is going to come from the set X, and the second coordinate is going to come from the set Y. So this is related to this. And let's see if you can figure this out. 2 is related to 4. Okay. 3 is related to 9. 4 is related to 16. Now we got some other ordered pairs in between here, and then the last one is going to be 10 is related to 100. Now let's close this up. Okay, this relation is a function. Right? This relation is a function because look, all of our first coordinates are all going to be different, even though I didn't write these in, but look at the pattern. Now we can actually represent this by this equation here. this over a little bit. So this is how we are defining our relation. In other words, I'm taking 1 and I'm plugging it into 1 squared, and I get 1 out. So 1 is related to 1, and this is how we're defining the relationship right here. Take 2, plug 2 in, 2 squared is 4, right? We get 4 out. Take 3, 3 squared is 9. Plug 4 in, 4 squared is 16. And the last one, of course, you know, we got all the ones in between here, but we're not writing them, like 7, 8, 9. 10, plug 10 squared in, you get 100. So 2 is related to 4, and we've defined our relation by this equation right here. Now, there's a way of writing this. Instead of having to write all of this out and writing this here, we're going to use what's called set builder's notation. Okay, set builder's notation. So I'm going to label this once again as, let's say, SQ, and by the way, that stands for the set of all squares. You know, that's what SQ is short for. And this is how I'm going to define my relation. We're going to have the set of ordered pairs such that, this line right here means such that, this is what we're defining our relation, y is equal to x squared. And then this over here is going to be, this is going to be what's called our domain. Okay, now that's something that I haven't mentioned yet. Also, we want to say that x is an element of, let's say, n. And I have a section on sets. Well, anyway, n is the set of natural numbers, you know, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and goes on forever. Anyway, so this is our domain right here, and I'm defining what x is right here. It's between 1 and 10. Alright, so this is set builder's notation, and of course, this, you know, we wouldn't want to have to do this. What happens if we were going to 10,000, right? We wouldn't want to have to do that, okay? Set builder's notation, the set of all ordered pairs such that y is equal to x squared, and then I've defined what my domain is over here. Now the domain, I don't guess I've mentioned what domain is, but this right here, for example, is our domain. Okay, the domain, this is our domain, and this set here is our range. Okay, this is the range, and this is the domain. Alright. I don't know. I guess I should give some more examples of using some set builder notation. I think we'll do that. Let's clear this out. Okay, let's say that we had the set, I'll call it V this time, the set of ordered pairs x, y, such that y is equal to x squared plus 1. Alright, and I'm just going to say that in our domain we're going to have negative 1, 0, 1, and 2. Alright, so that's our domain. Let's see what this set actually looks like as a set of ordered pairs. So if I were to take negative 1 and I were to plug it in right here, negative 1 squared is 1, and 1 plus 1 is 2, right? So we plugged in negative 1 and we got 2 out. So that would be one of our ordered pairs. Plug 0 in, 0 squared plus 1 is 1. So we plugged 0 in and we got 1 out. Plugging 1 in, 1 squared plus 1 is 2. So we plugged 1 in and we got 2 out. And last one, plug 2 in, 2 squared is 4, and 4 plus 1 is 5. So 2 and 5. So let's identify our domain. Our domain is negative 1, 0, 1, and 2. And our range, this is what's in our range, 2, 1, 2, and 5. Okay, so it looks like the largest number in our range is 5, and the smallest number in our range is, it looks like 1 here. Okay, all right. Alright, let's look at another example. I think I'm finished talking about this one. You know, I split these videos up and then I forget what in the world what I just talked about. Okay. Good enough. Alright, let's look at another relation. Now, I don't know if I mentioned, so that last relation was a function, okay, because all the first coordinates were completely different. Let's see if you can tell me with this relation, and you know what, I'm just calling this the set R here. So it's the set of ordered pairs such that y squared is equal to x, and our domain is going to be x is equal to 0, 1, and 2. That's going to be the only thing, the only numbers in our domain. I'm just, choosing three things. Trying to make it short, but at least get the concept through. So let's go down here. Y squared is equal to, now 0 is my x, so I'm plugging 0 in here. What numbers can I plug in for y to get 0 out? Well, the only number is going to end up being as 0, right? 0 squared is equal to 0. So, in other words, I plugged in 0 for my x and 0 out for my y. Okay? Now let's look at this other one here. We have y squared is equal to 1. So what number can I plug in and square and I get 1 out? Well, I know that if I plug 1 in and I square it, I get 1 out. So we know that 1's related to 1. And there's another one. I can plug negative 1 into y because negative 1 squared is 1 also. So 1 and negative 1. Now keep in mind these numbers here, this 1 here, right? This is our x's are the domain, okay? Even though it looks like I'm plugging numbers into y, that's coming from our range. Alright, let's do one more here. Y squared is equal to 2. Well, I know that if I were to plug in the square root of 2, because if I square the square root of 2, I get 2 out. And so therefore 2 being my x coordinate and the square root of 2 being my y coordinate. Also, if I were to plug in negative square roots of 2, I get a positive 2 out also. So you see there's two numbers, 2 and negative square roots of 2. Alright, well, try to make this short, so the domain is a 0, 1, and 2. Now let's look at this if we were to write R as the set of ordered pairs. So R is equal to, right, so the first one would be 0, 0. And then we could write 1, 1. And by the way, it doesn't matter what order you write these in, but we're writing it in this order right now. And of course you have 2 square roots of 2 and 2 negative square roots of 2. And I believe that's all of them. Okay. Alright, well, let's look at this relation. Question is this relation a function? And the answer to that is no, because you see our first coordinate here is a 1. We have another ordered pair in this set where the first coordinate is 1. So this is not a relation because remember, not a function, because in a function these first coordinates must all be different. Okay. So we could say that, right, so this is not a function. Okay. That relation there is not a function. But let's look at the domain. Let's look at the domain here. So the domain, what's in the domain? Well, we define the domain up here as 0, 1, and 2. But what is in the range? The range is going to be 0, 1, So we have 0, 1, what else is in our range? -1, square root of 2, and negative square root of 2. Okay, but usually when we talk about domain and range, we're specifically talking about functions. But that's okay. We can consider, our domain comes from our first coordinates, and the range comes from the second coordinates. Right, so that's what we got to remember, and also that this is not a function. This is a relation, but this is not a function. All right. I think that's going to end this section on functions and relations, and into the next section we're going to get into actually graphing linear equations. All right, or I guess you should say we're going to graph linear functions. Anyway, so that's going to end this this part of relations and functions.